I think I'm part of the group of scientists who started off as being fascinated by astronomy and by stars and space and everything like that. So when I was 12 years old, I joined an astronomy association.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth.
So I'm Wouter Deconinck. I'm a professor of physics in the physics department at William & Mary. My research is at the Jefferson Lab. I work on an experiment called the Q-week experiment, and that runs at Jefferson Lab, a national lab in Newport News. We generate electrons in a photocathode. So those electrons we accelerate in an electric field. Then after they've been accelerated, we use superconducting cavities. So then instead of using two plates with high voltage between them, we use microwaves.
But now there's Ward's incredible microwave oven. It'll defrost, simmer, bake.
And so you get high fields and low fields and high fields and low fields, and we make sure that the fields change in such a way that the particle is always on the crest of one of those waves. And so it basically serves down this wave. That's what happens in the straight sections of the accelerator. In the bending sections of the accelerator, we bend them using magnets. Those magnets don't change the energy of the electrons, they just bend the directions. So in Q-week, the beam enters the Hall. So our main detector technology that we use here consists of quartz detectors. So we have 2-meter long quartz bars. When an electron flies through those quartz bars, a little bit of light is generated. It's a chunk of light similar to the supersonic boom of an airplane that flies faster than the speed of sound. So this light travels along those quartz bars, and at the end it's detected and changed into an electrical current. We turn those currents into digital signals, into numbers, and those numbers are then what ends up in data files. The electrons that interact in the target, they fly off in all directions, but we're only interested in the ones that have a particular angle and a particular energy. So to select the ones with only a particular angle, we use collimators, so basically thick lead alloy slabs with very precisely cut out holes, so we know exactly which electrons make it through, and they select the angles that we're interested in. And then after those collimators, we have a magnet system, and so what happens is that high energy electrons just go straight, low energy electrons, they get bent more. We end up with a pure sample of electrons which has a known energy and a known angular distribution. So hopefully, well, I'm a scientist, I'm not supposed to have feelings about one result versus another, but hopefully we will measure something that's different, because that would be very exciting, because then we open up an entirely new avenue of research, and we open up this question, why is it different? And there's the goal of knowledge. We're just collecting, or we're creating knowledge. We're finding out things about the universe, about nature, about how physics work, how objects are composed, that in no other way would we be able to find that out. I'm still learning a lot, and that's certainly not something I miss. I think that's something everyone should keep on doing and keep on enjoying. And in the end, that's what makes us human, I guess, that we learn and we take new knowledge and apply it. Hobby, I'm a professor. I don't have any time for all that. Oh, we don't do a lot of scantrons, no. I prefer open-ended questions. If I had my pick, I would have all of you do oral exams, so you would just talk and no writing. doing doing analysis and which involves writing a lot of code, programming code, that tends to work better under hard rock music. Belgian French fries, of course. But French fries are Belgian, that's why they're Belgian French fries.